In this course, we're going to have basically 12 outcomes. Some of those involve quite a number of lessons or number of details, but these are basically the things that you're supposed to know for this course. So in studying for the exam, you can go through and say, yep, I know how to do this, I know how to do that, and this is where I generate the questions from. So hopefully this helps you, and I would suggest that you kind of go through this, back to this as you study. So today's class, to start off, what we're going to do is we're going to just basically do a review so that we know the basics, and we're able to use these later on in the course. For instance, a lot of the things that we do today are going to come down and be involved in, for instance, when we solve logarithmic equations. Now that's actually pretty complicated stuff, but ultimately it ends up, the very end result is having to solve an equation for a variable, which is what we'll go through today. So this lesson is going to permeate throughout the entire course. And so it starts with some terminology and definitions, and I'll do an example or two of those as well. So the first thing we have here, and again, this might be a review, this hopefully is a review, but it's important to have the same common language here. The first thing that we're going to look at is what exactly a variable is. If you are like most math students, when we started adding variables in letters into math, that's when it got a little bit confusing. But a variable is simply a letter that can stand for a number that can change. So I can't use the number, I can't use a symbol like this to represent a variable, because this is already the number 7. We know what this means. I could use a lightning bolt, or I could use a smiley face to represent a number. But we don't usually do that. We usually type letters in. And so what we have here is x, of course, that's our famous one. And so x in the 2x minus 6 is a variable. X could be any number I wanted it to be. And sometimes we'll have to solve for that. And so these variables are related to each other in what's called a function. And a function is just a relationship. So y equals 2x, that means that whatever the x is, y is going to be twice that value, always. In a different relationship, y might be 1/3 x, or it might be y equals 2x squared plus 4x. These relationships can get complicated, but ultimately what we have here is a relationship defined mathematically. And so this is a function is a generator. It's a number generator. This function y equals 2x generates the function y, generates the number y, I should say, for whatever x value. You give me an x value, I can then plug that into my function and get out a y value. Now sometimes these questions can come down to evaluating an expression. What that means, evaluating, means get the value of. You'll hear me say this a lot. You should always ask yourself, what does your answer look like? Is your answer a graph? Is your answer a function? Is your answer a number? Well, when we ask you to evaluate an expression, we're asking you to get the value of the variable. The value of the expression. And so what we're looking at here is a number. My answer is going to be a number. So if I have the expression 4x minus 1, and then that's a minus 1, and then I plug in x equals 3, well, anywhere I see an x, I'm going to plug in a 3. And so now to evaluate this, we have to follow the order of operations. So the order of operations is a quick way of us remembering this bed math, is a quick way of us remembering this. Okay, welcome to the first class of the University Prep course. These are your 12 outcomes. Although not all of them are of equal value, and some of them are pretty complicated. These are basically what you're supposed to know for this course. So when you're studying for the final or for the midterm, you can come back to these and say, okay, yeah, I know how to solve systems of equations, for instance, and I know how to do this and this. There are different colors here because basically, for the first two, we're going to do those in this session. And then identify linear and quadratic exponential patterns. Number 3, that's going to happen throughout the course. We're going to do some of that next week and then some of that much later on. And same thing with the number 4 there. Numbers 5 to 8 basically are the heart of your quadratic unit. 9 and 10 are your exponential units, and then 11 and 12 are your probabilities. So what happens here is that you can come back to this and really identify what you know and what you don't know. That's the hope here. These are kind of like your learning targets. If you don't know how to, for instance, transfer between 3 forms of quadratic, well then that's going to be a test question. You have to make sure that you know how to do that, and that would be where you would perhaps post something to the discussion board so that I can go over it. Even though I might have already gone over that material in a session, that still might be a confusing issue for you. So you would ask there. Before we get into our targets for tonight, the solving linear equations and solving a system of equations, we need to have a common language. If you and I aren't talking the same thing, it's going to be awfully confusing, especially since we're not face-to-face. So what we'll do here is we'll look at some phrases or terms, their definitions, and then I'll give you an example of each one. This is supposed to be a review. Hopefully it is. If it isn't, well, this is why one of the reasons why we're doing this. But what I want you to realize is that all of the things that we get to in this course are going to come back to the skills that we do tonight. So make sure that you're able to do these and you're comfortable with working the math like we're doing tonight. So let's take a look at the first phrase or term, and that's a variable. You might be like myself and most math students. You felt math was fairly easy until they started adding in these letters, and then of course it gets difficult. But really all a variable is a value that can change. So for instance, your height is a variable up until a certain point in your life. You grow to a certain height and then your height remains constant. And then I guess as you get older, if you're lucky enough to get old enough that you start to shrink, well then your height is variable again. But we're going to represent these variables with letters. Now I couldn't, for instance, use the number 7 to represent a variable because we already have a meaning for that symbol. I could use a smiley face, I could use a lightning bolt, I could use a squiggly line or something. Those could be representative, or those could represent numbers, but those are difficult to type, and so we just use letters. And in fact, of course, as you're probably familiar, we use X a lot. And I can hear some of you shuddering a little bit now, but it's not that bad. What I want you to recognize is that X just is any number. So, for instance, in the example 2x minus 6, X is the variable. And so X could be any number I want it to be. Now, I don't know what X is, so I don't know what 2x minus 6 is. But if I gave you an X value, you could tell me what 2x minus 6 is. Now, these variables are going to be, get rid of that, are going to be represented, or are going to be related to each other in what's called a function. Why can't I get rid of this? Well, let's put it up here. So a function is the relationship between two variables. X and Y are traditionally the variables we use, but we don't have to. Tonight we won't use those only. And when I teach physics in high school, I try not to use X and Y because they don't have any meaning. So what we look at is this relationship between these two variables. It might be the time and the height of a ball, so I would use T and H there. It might be the cost per number of units sold, and so I might use C and N as my variables. But if we're just practicing and there's no real meaning to these variables, then traditionally we just use x and y. So y equals 2x is the relationship between the variables x and y. What happens here is that in this function, or this relationship, the function itself tells us that whatever x is, y is always twice that amount. And so a function is a number generator. It's going to tell us what number y is given any x value. But ultimately, this is a relationship. We're going to evaluate an expression a lot in this course. What that means is to find out the value of the expression when you know what the variable is, the value of the variable. So when I see the word evaluate, that's going to mean get the number. So you'll hear me say this a lot in this course. What's your answer going to look like? Is it going to be a function? Is it going to be a graph? Is it going to be a picture? Is your answer going to be a number? And when I say the word evaluate, your answer is going to be a number. This means get the value of. So for instance, we have 4x minus 1. There's our expression. It's not a function because there's only one variable, but it's an expression. And if we know x equals 3, then wherever I see an x, I can plug in the number 3. And so to do this, we've got to make sure, to evaluate this properly, we've got to make sure we're talking the same thing. For instance, if I have 4x minus 1 and x equals 3, anywhere I see an x, I'll plug in a 3. Well, you might look at this and you might say, oh, okay, well, I can do this. I know that 3 minus 1 is 2. I'm not saying that this is the correct way to do this. But you might say that 3 minus 1 is 2, and so you have 4 times 2, that equals 8. Somebody else might say, yeah, but 4 times 3 is 12, minus 1 is 11. So here we have the same expression, we have the same value for the variable, but we get 2 different answers. And so this is not mathematically helpful. We need to be all talking about the same language. So mathematicians have figured out a way, or have decided on a way, to communicate. And you've heard this before, I'm sure. This is called the order of operations. It has a little mnemonic here of bed mass. And I think it's important that you realize that you're not supposed to look at this and go, oh, I get this. Yeah, this makes sense. This doesn't make sense. It's not supposed to make sense. This is a convention. This is something that they decided on. I don't know exactly who they is, but they've decided on this. For instance, in Canada, we drive on the right side of the road. That doesn't make any sense. We just do it. That's what they decided. There's other conventions, for instance, that you sit at a table for dinner. Does that make much sense? We could have sat at an ottoman. We could have stood up and had our dinner. Right? That's kind of maybe a bad example, but there are conventions here. Here's a convention with dinner. You have a fork on the left-hand side of your plate when you go to sit down. Even though we pick it up usually with our right hand and we start eating with our right hand, by convention, we put the fork on the left. It's not supposed to make sense. It's just that's how we do it. So this is the exact same thing here with the order of operations. In order for us to go and get the exact same answer here, 8 or 11, only one of us is right here. We have to deduce the meaning of this 4x minus 1. Does it mean to take 4 and multiply it by x and then subtract 1? Or does it mean take x and subtract 1 and then multiply that by 4? So we do this order of operations. That way we all know what we're talking about. And so this is the order in which you would do these operations. Brackets, you do any brackets first. You do your exponents, then your division, then your multiplication, your addition and subtraction. So when we go back to 4x minus 1, when x equals 3, now we know what we're talking about. Anywhere I see an x, I'm going to plug in a 3. I see that there's nothing inside my brackets to do. There's just a 3 there. There's no operation. It's not 3 plus something or 3 times something or whatever. So I'm done the brackets. There's no exponents. Now I'm into division and multiplication. So I'm going to multiply first. So 4 times 3 is 12, minus 1 is 11, or And then I'll subtract 1, which gives me 11. So that is the meaning of 4x minus 1 when x equals 3. Had I wanted to get the answer of 8, what I would have to do there is say, okay, take the x and subtract 1 from it first. And that's why I'd have to put that in brackets. Again, that doesn't make any sense. We have just decided this. We're just talking, we're just communicating mathematically, and this is what we've decided on. So now we can see I have to do my brackets first. So I'm going to plug in my x equals 3. Now there is an operation to do in my brackets. 3 minus 1 is 2. And now I will multiply to give 8. So by understanding the order of operations, or you can't understand it, by knowing the order of operations, we now have a way to communicate with each other. Okay, so it's not supposed to make sense. It's just a convention. It's just a way that we do things. For holiday traditions, for instance, some of these holiday traditions don't make any sense. It's just the way that we do them. And so this is the same thing here with bed mass. So let's take a look at a few examples here. I'll do these out. In the face-to-face course, what usually happens here is that I would do 1 or 2 of them out and then give the students a chance to do them, and then I would go over them if they, and then answer questions. So what I would suggest probably to do here is that you could watch me do 1 or 2 of these, pause the video, and then try them yourself. I really think that you have to do math to get good at math. I make the comparison to hockey. I started playing hockey when I was 25. But before that, I watched a lot of hockey. I watched the best players in the world play hockey. I read books on hockey. I watched other people play hockey. And I thought that that would make me a good hockey player. And of course, that was terrible. So what happens here is the same thing in math. Just by watching me do the math, I'm actually quite good at math. Watching me do math doesn't make you good at math. Just like me watching Sidney Crosby, who's a professional hockey player, play hockey, that doesn't make me any better. I'm a professional math teacher, believe it or not. And so watching me do this math, or watching the math happen on the screen as I do it, doesn't really help you. The only way to get help is to actually try it yourself and then go back and see what I've done and compare. Even if you get it wrong, you're still learning there. So I'm going to go over the first 2. Well, I'll go over all these, but I suggested let me go over the first 2, and then you can pause the video and try some of these yourself. So the first one, I have the expression 7x minus 3 when x equals 7. So whenever I see an x in my expression, I'm going to plug in a 7. I like to put that in brackets. Obviously, I don't want to put 7, 7. That looks like 77. And I don't want to say 7 times 7 with the multiplication symbol. Okay, because that just looks like I've got still an x here. Okay, I don't want to do that. So I'll just put it in brackets. Now, using the order of operations, I'm multiplying here, so this is 49. Then I'll subtract the 3, and so 49 subtract 3 gives me 46. Now question 2, I have 10 times x minus 2 when x equals 4. And so what happens here is that, again, anywhere I see an x, I'm going to plug in a 4. I have to evaluate the brackets first. Not because it's mathematical, it's because that's how we decided. That's what we decided. So 4 minus 2 is 2. 10 times 2 is 20. So now I'll do question 3. Maybe I'll do that up here. Question 3 is 5r minus 7t minus 6. If r equals 2 and t equals 1. So anywhere I see an r, I'm going to plug in a 2. Anywhere I see a t, I'm going to plug in a 1. I'm going to multiply first. Now I'm going to subtract. 10 minus 7 is 3, minus 6 is negative 3. Sorry, that should have been a negative 3. So 5r minus 17 minus 6, when r is 2 and t is 1, is equal to negative 3. So now I'll try this one. Let me get a new page here. So 3t squared plus 5t minus 9. 3t squared plus 5t minus 9. And that's when t equals 2. So wherever I see a t, I'm going to plug in a 2. Now to do the order of operations, I have to do my brackets first. There's nothing inside the brackets. I'm going to do my exponents next. This is 2 squared. It's not 3 times 2 first. That's multiplication before the exponent. I have to do the exponent first. So this is 4. Now I can do the multiplication, 12, 10, and now I can do the addition and subtraction. So 10 minus 9 is 1, plus 12 is 13. I think this was question 4. Now question 5 is 3x times x minus 2 plus x over 2. 3x times x minus 2 plus x over 2. And we want to evaluate this when x equals 4, I think. So, again, you won't be surprised, but anywhere I see an x, I'm going to plug in a 4. And so I'm going to evaluate this using the order of operations. So I have to evaluate my brackets first. This is 3 times 4 times 2 plus 4 over 2. Now you certainly could, because you might get used to this and see, okay, yeah, that's going to be a 2 and this is going to be a 12. You can certainly do those first, or do those as well. But I'm kind of doing this specifically in the order of operations without kind of combining steps. So now I see that I have multiplication and division before I have the addition. So I'm going to multiply these together, and then I'll divide these, and then I'll add. So 3 times 4 is 12, times 2 is 24, plus 4 divided by 2 is 2, and so the answer is 26. So this is the expression, and the variable here, it was in 3 different spots. When that variable is 4, remember the variable means that it could change, but when it's 4, the expression gives me a value of 26. And question 6 is j plus 5 over 2 minus j. J plus 5 over 2 minus j. And we're trying to evaluate this. Oops. There we go. Sorry about that. We're trying to evaluate this when j equals 3. So I'll plug in j equals 3. Now what's happening here is there's a fraction for the first time. And again, something that they decided on was that when you have a fraction, there are implied brackets in the numerator and the denominator. They won't be written, but they are implied, which means I have to evaluate the addition here. This is really 8 over 2 minus 3. Now there's nothing to do inside these implied brackets, so 8 divided by 2 is just 4. Now I'll subtract 3, and I get the answer of 1. So j plus 5 over 2 minus j when j equals 3 gives me a value of 1. And you can see the answers are there. Okay, so another very important phrase here is going to be solving an equation for the roots, or solving an equation, I should say, or finding the roots. So what this means is that we're going to take an equation. So first of all, an equation has an equal sign. It's a function, and we're going to find out the value of the variable when we know what that equals. So we're kind of doing the opposite of what we were just talking about. We were just talking about finding the value of the expression when we knew the variable. Now we're trying to say, well, what would be the variable that would give me this value? And so, for instance, if I have 3x minus 4 equals 8, what happens here is that I'm looking for the value of x so that this expression gives me a value of 8. And so to do that, I'm going to undo BEDMAS. So what we would do when we undo anything is we would start at the end and go backwards. For instance, I always use the example of getting dressed in the morning. When you get dressed in the morning to go out to work, the last thing you put on might be your shoes. Well, when you get home to get undressed, the first thing you take off is your shoes. Otherwise, you're doing that pants dance, your pant legs caught in your shoes and stuff. We've all done this, trying to rush. Anyways, so we're going to undo what's being done. So that means I'm going to actually start with the addition and subtraction. Then we'll move on to the multiplication and division, then do the exponents of the brackets. So if I have 3x minus 4 equals 8, my answer is going to look like x equals a number. So I'm going to undo what's being done. So if you're stuck here and you don't know where to go, ask yourself what's being done. For instance, what does it mean to write 3 in front of x? Well, that means I'm multiplying by 3. And this symbol, it's supposed to be that symbol anyways, that symbol means I'm subtracting 4. Well, I know how to undo those, and I think you would too. You undo multiplying by 3 by dividing by 3. And you undo subtracting 4 by adding 4. And what you need to remember is that this is an equal sign. This is an equality. One side equals the other. And so whatever you do to one side, you have to do to the other side to keep it equal. Just like in my family, I have a few boys in my family. I have 3 boys, but the 2 of them are old enough to be jealous and things like that. So if I give one boy a toy, I have to give the other boy a toy to keep it equal. If I give one boy a candy, I got to give the other boy a candy. If I give one boy a timeout, I got to give the other. Well, it doesn't always work, I guess. They don't always want the same thing. But in any case, here we have to do the same thing to both sides. So I'm going to undo both of these, but I have to do it in this order, this backwards order. So I'm going to start with my addition and subtraction. So I see that I'm subtracting 4. I'm going to undo that by adding 4. If I do it to this side, I have to do it to that side. And so I have 3x minus 4 plus 4 is 0, so I just have 3x on that side. And then here I have 8 plus 4 is 12. Now I'm going to undo what's being done. I'm multiplying by 3. I'm going to undo that by dividing by 3. If I do it to this side, I've got to do it to that side. 3 divided by 3 is 1, so I just have 1x, which we just write as x, and 12 divided by 3 is 4. So I can check this. I can plug in x equals 4 into that expression and see if I get the answer of 8. So this is a check. 3 times 4 minus 4. Now, because I'm evaluating, I'm going to actually do BEDMAS. So I'm going to multiply first. This is 12, subtract 4. This indeed equals 8. And so I know I have this correct. So again, here's some practice problems. You can pause the recording and try these yourself and then see how you did, whatever the case may be. I do strongly suggest that you try these yourself. So I'm going to go over these, solving each one for the variable. My answer is going to be x equals a number, or question number 2 is going to be w equals a number. That's how I'm going to know that I'm finished, when I have x equals a number. So in this case, I'm doing 2 things to x here in question number 1. I'm multiplying by 5, and I'm subtracting 4. And so I'm going to undo BEDMAS. In fact, I'm going to write that out to remind us. So what I see here is that normally I would be, like in this example up here, I started adding 4 to both sides first. As you can see there and there. But here it's a different scenario because the x minus 4 is in brackets, and I can't get inside those brackets till the very end. So now I'm going to divide everything by 5 to begin. So 5 divided by 5 is 1. So on the left-hand side I have x minus 4. On the right-hand side I have 2. Now I will add 4 to both sides. Maybe. And so I get x equals 6. In question 2, I'm again multiplying the w by 8 and subtracting 2. So I will undo subtracting 2 by adding 2. And so I'll have 8w equals negative 40. Now I'll divide both sides by 8. So I get w equals negative 5. Now, let me add a new page here. In question 3, I have 1/2 times g plus 1 equals 6. So 1/2 g plus 1 equals 6. So what I'm doing here is I'm going to, again, identify what's being done to the variable. I'm adding 1 and I'm multiplying by 1/2. I notice the adding 1 is in brackets, so I can't undo that till the very end. So I have to undo multiplying by 1/2. So I'm going to undo multiplying by 1/2 by dividing by 1/2. Now this is where it gets a little bit tricky because you have to realize what you're up to here. You're asking in this question right here, in this section right here, you're saying, if I have 6 of these squares, all the exact same size, as you can tell I've carefully drawn those, I'm asking how many times does half, which would represent here, go into those 6? And you can see that it would happen 2 times per. So what happens here is that dividing by a fraction, I actually flip and multiply. Now I'm not getting angry there and swearing. I'm not saying you flip and multiply. I don't have anything against multiplication. I'm saying you flip and multiply. You flip the denominator and multiply. And so what I would have here is 1/2 divided by 1/2 is 1. So I have g plus 1. And here I have 6 times 2. That's going to give me 12. By the way, if you're doing this in your calculator, this 6 divided by 1/2, you have to type this in. 6 divided by bracket 1 divided by 2. You could certainly type in 6 divided by 0.5. But I want you to recognize that if you just type in this, 6 divided by 1 divided by 2, your calculator does the order of operations. So it takes 6 and divides it by 1, and that's just 6, and then divides that by 2, and that gives you 3. This is correct, but it's not what we wanted. We wanted 6 divided by 1/2, which is 12. And so now I'm going to subtract 1 from both sides, and I get g equals 11. Okay, so now let's take a look at question number 4, which we have 3x plus 6 equals 9x minus 4. Now some people get stuck in this one because it's a little different than the other ones. And so one of the things that I would suggest you ask yourself if you're stuck is, why exactly am I stuck here? What is it about this question that I don't get? And here you'd see that you have 2 x's. They're still the same variable, but they're in 2 different spots. So what we could do here is we could subtract 3x from both sides. And 3x minus 3x is 0, so I just have 6 on this side. And here I would have 6x minus 4. So now, just by subtracting 3x from both sides, which we're allowed to do, we're allowed to do anything to both sides as long as we do it to both sides. Since we've done that, we now have gotten this into an equation that we're used to. Now I can see that I can start undoing what's being done. I can start to add add 4 to both sides. So I have 10 equals 6x. And now I'm going to divide both sides by 6, and I get x equals 10 over 6. Okay if you leave it like that, but that does reduce to 5 over 3. And it's certainly okay if you get this in your calculator. I think this is 1.667, or something to that effect. So any one of those is an appropriate answer. Now to question number 5. We have r plus 4 over 3. Subtract 1 equals 9. So what happens here is, again, I'm going to undo BEDMAS. So I see that there are 3 things that I'm doing. I'm subtracting 1, I'm adding 4, and I'm dividing by 3. However, I have to remember that because this is a fraction, there are implied brackets here. So I'm going to undo what's being done by adding 1 to both sides. So I have r plus 4 over 3 equals 10. Again, imply brackets. So I have to multiply both sides by 3. So I have r plus 4 equals 30. Now I'll subtract 4 from both sides, and I get r equals 26, which is the only root to this equation. If I plug in 26 in for r, I'll get 9 equals 9, which is a true statement. And then in question number 6, we have 7m minus 4 equals 2m minus 19. So again here, there's the same variable, but it's in 2 different places. So I will subtract 2m from both sides. This is called collecting like terms. Both of these are m's, so they are like terms. So I have 5m minus 4 equals negative 19. So 5m, as I add 4 to both sides, 5m equals negative 19 plus 4 gives me negative 15. Now I'll divide both sides by 5. And so m equals negative 3. So that's what solving an equation looks like. We're going to undo what's being done to the variable. So let's take a quick peek at where these functions come from. You have relationships, all over the place in your daily life. If you're looking at traveling on a road trip, then you would have a relationship between the velocity, average velocity, or average speed, and the distance you travel and the time that it takes. If you're looking at filling your gas tank, you have a relationship there between the amount of gas and the cost that it costs you. There's also a function to relate the degrees Celsius to degrees Fahrenheit. So the temperature in Dallas, Texas, let's say is 94 degrees Fahrenheit. What is the temperature in degrees Celsius? We're going to figure out how to do this. And I remember, I'll say we know this. We know that when it's 10 degrees Celsius, it's it's 50 degrees Fahrenheit. And when it's minus 40 degrees Celsius, it's time to move. It's also minus 40 degrees Fahrenheit. It's actually, those are the same measurements. So when it's minus 40, it doesn't matter if you're talking Celsius or Fahrenheit, it's just cold. So if we know these, And we know that it's a linear relationship, which means that anytime you increase the degrees Celsius by 1, the degrees Fahrenheit increases by the same amount. What happens there is we can get this equation. Now, math a lot of times comes down to looking at something in a different form. So I'll say things like we can translate from a picture to a graph to a word equation to a mathematical equation. In fact, I think you've been doing math since you're probably 6 months old. Perhaps your parents read you a book that had the number 5, and it had the word 5, and it had 5 little duckies on it. That's doing math. You're looking at the concept of 5 in 3 different ways. You're looking at it pictorially with the duckies, you're looking at it symbolically with the symbol for 5, and you're looking at it in terms of a language with F-I-V-E. And so what we're going to do is the same kind of thing here. We can look at this graph and recognize that there's a relationship between the degrees Celsius and the degrees Fahrenheit. This graph tells us everything there is to know about how, what temperature Celsius it would be, gives me what temperature it would be in Fahrenheit. I can get that from this graph. The problem with this is that it might be difficult to read, or it might be inaccurate. So we're going to come up with the same information, just done in an equation. So the equation of a line has 2 parts to it. It has the slope, which for some unknown reason to me, we give it the symbol m. People will say that's Latin, but I don't know if that's a cop-out or not. And we also have the y-intercept, and that's the b value. Okay, again, it's just what we call it. So y equals mx plus b describes any straight line. Sometimes I'll ask, what's the equation of this line? And your answer is going to look like y equals mx plus b. So in order to figure out this equation, we're going to need to solve for 2 things. We're going to need to know the slope of the line, and we're going to need to know the y-intercept. Once we have that down, if we go back here, once I have the slope and the y-intercept of this graph, I know everything there is to know about this graph. I'm translating this from a picture to mathematical symbols, i.e. an equation. So here's the idea of a slope. The slope of these 4 graphs is all equal. It's telling you that the variables, for a change in x, they go up the exact same amount in the y value. For whatever change in x there is, there's an equal change in y for all of these graphs. And here's the y-intercept. These all have different slopes, but they all cross the vertical axis at the same point. We call this the y-intercept. There's nothing really special about the y-intercept. It's just an easy point to reference. So what we need to do here is we need to identify what the slope is and what the y-intercept is. So to find the slope, we're going to take the change in the dependent variable and divide it by the change in the independent variable. In other words, we're going to take delta y divided by delta x. And delta just means change in, so this is y2 minus y1 over x2 minus x1. This is your slope. In calculus, the slope is one of the crucial points to the entire course. You're trying to find the rate at which things change, which is called the slope. Now here we're going to talk about linear slopes, so that the rate is always the same. Okay, but in other scenarios it certainly won't be. So let's find this slope. So first of all, what I have here is I have an x1 and a y1, and I have an x2 and a y2. We just label these 1s and 2s just to differentiate them. I don't want to see an equation like this, y equals y, or y minus y. That's going to equal 0. That's not helpful. So what I'm going to say here is, to find the slope, we're going to take one y and subtract the other, and then divide by the x values, the difference in the x values. The key here is that whatever you pick for y2, you have to pick its x value as x2. So I've picked -40 as my y2. That means right away my x2 is also this -40. y1 I'm going to subtract from this, so y1 is 50. x1 is its x value, which is 10. So in this case here I have -90 over -50, which reduces to 9 over 5. What this tells me, by the way, is that for every an increase in 5 degrees Celsius results in an increase in 9 degrees Fahrenheit. So there's my slope. So right now my equation looks like this. Y equals 9 over 5 x plus b. Now x and y might not be as useful as maybe F for Fahrenheit and C for degrees Celsius. So now I'm left to find the y-intercept. So the y-intercept can be found if we know what the value is of the function when x equals 0. We can just plug in x equals 0 and get that. We don't know what that is in this case. And so what we have to do here is we have to find the y-intercept a little differently. Our equation again looks like this. Since we don't know the y value when x equals 0, we need to know an x and a y value to solve for b. Well, I know two x and y values. I know -40 and -40. There's one x, y value. I also know 50 for y and 10 for x. Now I can solve both of these equations. I'm going to multiply this out. -40 divided by 5 is -8. Times 9 is -72. I'm going to undo what's being done to b, so I'm going to add 72 to both sides, and I'll get 32. Over here I have 10 divided by 5 is 2, times 9 is 18. Now I'll subtract 18 from both sides, and again I get b equals 32. It doesn't matter which one I use, which point I pick in, but if I'm trying to find the b value, I need to know an x and a y. When I do, I can solve this. So my equation now is y equals the slope times x plus 32. And this 32 means that when it's 0 degrees Celsius, it's 32 degrees Fahrenheit, which is what we see here. So now this relationship is exactly what we had with that graph. It's the exact same thing. They're just in different forms. One form is useful, more useful in certain scenarios, one form isn't. If I wanted to figure out our original question, which was if it's 94 degrees Fahrenheit, what is it in degrees Celsius? I would need a graph that goes up to 94 degrees Fahrenheit, and I have to be able to read this off, and it might become awkward and imprecise. But now with this equation, I can plug in f equals 94. So let's do that. If f equals 94, anywhere I see an f in my equation, I'm going to plug in 94. Now I'm going to undo what's being done. So I'm trying to solve for c. So I'm going to subtract 32 from both sides. And so here I'll have 9 over 5 times c, and this will be 62. I'm going to undo what's being done. I'm going to multiply both sides by 5. This gives me 310 equals 9c. Now I'll divide both sides by 9, and I get c equals, I think it's 34.4. Memory serves me correctly. Yeah. So you can see this was my line. here's my graph. This is the point down here, 40, or negative 40 comma negative 40. Here's the point 10 comma 50. If I continue along that same pattern, I get the point 34.4 comma 94. So when somebody tells you it's 94 degrees Fahrenheit in Dallas, you now know that that's really hot, 34.4 degrees Celsius. So let's look at another function. If we looked at the two variables involved in a very basic cell phone plan, we might consider that they would be the relationship between the cost of the bill and the time of usage. And of course, the time depends on the bill. So the time is going to be our X value, and the cost is going to be the Y value. Those are supposed to be quotation marks. I don't know what's going on there with my little marker, but anyways. So let's do an example here. Let's say that it costs 20 cents per minute and that you're always charged a monthly fee of $7. So we can answer a few questions here. So first of all, what's the function? And remember, function is a relationship. Mathematically speaking, that's an equation. We want to see an answer of C equals something. Well, this is not like the last example where I knew the two data points. Here I'm given this 20 cents per minute, and here I'm given this monthly fee of $7. So I'm assuming that this is going to be a linear relationship, so I have the equation y equals mx plus b. Well, what I see here is that this m value means that for every time the time goes up by a unit, like a minute, the c value is going to increase by that amount. And so what I see here is that this is my rate. This is my slope. The key word here is per. When you see per, you're thinking slope, because slope is the change in one variable per a change in the other. And so right now I have C equals $0.2 times the time plus B. Now this B value is what I would be charged if I didn't talk at all. If T is 0, then all of this term is 0, and I have the cost of the bill is just this B value. Well, if that was the case, and I didn't talk at all, I would still be charged this $7. So this $7 is the B value. So the function is C equals 0.2, I don't know what's going on there, 0.2 T plus 7. So in question 2, it says I talked for 45 minutes, what would be my bill? Well, what happens here is that here's the English version of this. That's difficult to figure out. The mathematical version, it's the same information, just in different forms. This is like the number, the word 5. This is like the number 5. I can use this to figure out, to predict the bill if I talked for 45 minutes. So let's do that. I would have C equals 0.2 T plus 7, and T is going to equal 45 minutes. So wherever I see a T, I'm going to plug in 45. Yeah, I totally messed that up. Sorry. C equals 0.2 times 45 plus 7. So 0.2, I'm doing this without a calculator. 0.2 is 1/5. 45 times 1/5 is 9 plus 7. The cost of the bill is going to be $16. Now, if the bill was $37.40, we can now figure out how long we talked. Anywhere I see a C in the equation, I'm going to plug in this $37.40. So now I'm going to undo what's being done. I'm going to subtract 7 from both sides. I'm going to divide both sides by 0.2. Now that's the same as multiplying both sides by 5 in effect. So this will give me 152 minutes. And so by using these equations, I'm able to predict the values of the equation at for certain times, or vice versa. Okay, the last thing we'll do tonight is we'll be looking at solving a system of equations. And so we can compare, for instance, to cell phone plans to see when they would cost the same amount. And we can do this when we have a systems of equations. Now, a system of equation is a set of equations that have the common variables. They're both dealing with cost and time, or they're both dealing with x and y. So if we take a look at an example here, if we have the relationship 3x plus 4 equals y, there is an infinite number of solutions to this one equation. I can pick any of these and they work. If I plug in x equals 1 and y equals 7, I'll get a true statement. If I plug in 0 and 4, I get a true statement, etc., etc. However, if I said that, yes, this was one relationship between these two variables, but there was another. If that's one and y equals negative 7x minus 1 is also another, now none of these solutions to the first equation work in the second. So they don't satisfy both equations. I'm looking for the x and the y value that satisfy both equations. So what I can do here is I can say, well, if they're both equal to y, and these y values are going to be the same, let's set these equal to each other. So I can set 3x plus 4 equal to negative 7x minus 1. Now that looks like one of the questions we did earlier, where we're going to subtract 3x from both sides and add 1 to both sides. And we get 5 equals negative 10x, and we divide both sides by 5. So we get x equals negative 0.5. Now what we can do is we can take this x value and plug it into either of the equations. This is the only x value that's going to give us the same y value in each equation. So it doesn't matter which variable, which equation I plug that into. In fact, I'll do both. If I plug in x equals negative 0.5 in the first one, I get y equals 2.5, and I get the exact same thing if I plug it into the other equation. So the solution here is x equals negative 0.5 and y equals 2.5. Now, that was a little bit of a kind of an easy scenario where they both were in the y equals mx plus b form, so we could just set them equal to each other. Sometimes they're not in that equation, not in that form, so we could put them in that form. But what we can do as well is we could do what's called substitution. And the key for substitution is that we're going to solve one of the equations for one of the variables. So if I take the first equation and solve it for y, and the reason why I'm picking that is it's quite easy to divide things by 2. I'm going to undo what's being done. I'm going to subtract 3x from both sides, ignoring this other equation for now. And then I'm going to divide both sides by 2. Now what I'm going to do is I'm going to substitute this into the other equation. And it's the key that it's the other equation. You don't want to plug this back into what it started. You're like a dog chasing your tail there. You're going to get a true statement, but it's going to be like 11 equals 11. Well, yes, that's true, but you didn't help me solve for the variables. I don't know what x and y are. So I'm going to take this and plug it into the other equation. Wherever I see a y in this equation, I'm going to plug in 11 minus 3x divided by 2. And now I'm going to solve for x. So you can see here what I did was, and again, there's a couple of different ways that you can do this, but I multiplied the negative 3 by 11 and then divided by 2 to get that. I multiplied the negative 3 by negative 3x to get positive 9x and then divided by 2. I looked at getting a common denominator here. 5x is really 10x over 2 plus 9x over 2. That's going to give me 19x over 2. And then I added 33 over 2 to both sides. Again, you can certainly use that in your calculator and get the decimal form there. It's apparently a lot easier to write it that way. But in any case, what I had here was 19x over 2 equals 95 over 2. So when I multiply both sides by 2, I get 19x equals 95, and I divide both sides by 19, and I get x equals 5. Now I'm going to take that and plug it in to find the y value. And so when I do that, I get y equals negative 2. Those are the only solutions to both equations. If I plug in x equals 5 right here and y equals negative 2 right here, I'm going to get 11 equals 11. And at the same time, I can plug x equals 5 right here and y equals negative 2 right here, and I'll get 31 equals 31. These two variables give me true statements, in both equations. And so this is substitution. You solve one equation for one of the variables, you substitute it into the other, and solve that equation. Make sure you solve for both values of x and y. So again, we can double check as we just talked about. When I do that, you see that this is exactly what I get. Oops. And there's also another way called elimination. We'll use this a lot during this course. So here's an example. We have 6h plus 3f minus 3 equals 6h plus 3f equals negative 3. And we also have 9h minus 2f equals negative 11. Well, if we subtract these equations, we get a new equation. But that new equation actually isn't very helpful because we have still two variables. We didn't eliminate any variables. So we can go and we can add these. Well, adding the equations doesn't help because I still have two variables. So what I'll need to do instead is I'll need to multiply both equations by something so that I get the coefficients of one of the variables to be the same. If I multiply the top equation by 2, doubling the entire thing, if I triple the bottom relationship, then what I'll see here is I'll have a 6f and a negative 6f. Please make sure to double and triple everything in the equation. It's like doubling a recipe. You don't just say, oh, I'm going to double the amount of eggs and not the amount of sugar. That tastes terrible. You need to double everything. So these equations now become 12h plus 6f equals negative 6, and 27h minus 6f equals negative 33. So now what I can do is I can add these two equations. When I do that, I'm going to get 12h plus 27h, which is 39. I'm going to get 6f plus negative 6f. That's 0f. I've eliminated the f value. And then on the right-hand side, I'm going to get negative 6 plus negative 33, which is negative 39. Now I can undo what's being done and divide both sides by 39. I get h equals negative 1. What I'm going to do now is I'm going to plug in h equals negative 1 into one of those two equations. When I do that, anywhere I see an h, I'm going to put a negative 1. I'm going to undo what's being done to solve the equation for f. I get f equals 1. So here, I'm able to take these two these two variables. I can plug them into these two equations and get true statements. So with elimination, what you do is you have to manipulate the manipulate the equations so that you get the coefficients to be the same of one of the variables. And then you add or subtract the equations, and then you can solve for that variable. And then you have to plug this into one of the first two equations, excuse me, to get the other variable. So we're going to do a quote-unquote real-life word problem. Just a note here, the reason why I'm picking these terrible examples is because in order to practice the math in a real-life scenario, you'd have to know something about science, or you'd have to know something about business, and I can't assume that you know those things. So I want to do something that's very straightforward and kind of not real life at all, just to practice the math. So this is a ridiculous question, right? A certain math textbook costs $10 more than 3 times the amount of an English book. Together they total $140 before tax. Calculate the price of each book. No, I'm not going to calculate the price of each book. I'm going to look at the barcode, or I'm going to look at the price tag, and I'm going to ask somebody at the store, or I'm actually going to question why I'm buying an English book in the first place. But anyways, enough about that. Everybody understands, I think, the idea of buying textbooks or buying books, and it's very universal. So I don't have to worry about you knowing anything about physics or biology or economics to do this question. So that's why these real-life word problems are pretty lame, is because I don't know what everybody's real life is. So we're going to kind of go to the lowest experience, or the simplest experience we could all have, and just practice the math. So let's take a look at this riveting question. First of all, I need to define my variables. And I'd like you to be specific when you do that. Don't tell me that M is for math. That's not a variable. Remember, a variable is a number, and we're trying to figure out what that number is. So math is not a number. Math is a word. I could say that M equals the cost or the price of the math book. That's a number. And E is the price of the English book, let's say. So now what I'm going to do is I'm going to translate. Here's a sentence, here's a relationship in English, and I'm going to try and translate this into math. So a certain math book or textbook costs, well, that's going to be M equals $10 more than, so I'm going to take 10 and add it to 3 times the amount of an English book, 3E. If you're stuck with that, try a simple example. Say the English book costs $10. Well, what's $10 more than 3 times $10? 3 times $10 is $30, plus 10 is 40. That's exactly what we did in this equation. So sometimes adding a number to it, although that number is made up and probably not right, still can help you. So there's my first equation. Together they total $140 before taxes. Well, what happens here is that together, I'm buying them together, so that's M plus E. That's going to equal 140. So here I have a system of equations, and I know that because I've got 2 equations with the exact same variables. Now this is already solved for M, so I can plug that into here. Wherever I see an M in the second equation, I'll plug in 10 plus 3E. I'll collect like terms. Now I can solve for E. Since I have this E value, 32.5 or $32.50 for an English book, I'm going to now plug this back in here, and I'll get the price of the math book. The math book costs $107.50, which is, of course, money well spent, especially if you're spending $32 on an English book. Just go and watch the movie. Actually, wait a second. You guys are kind of watching the movie right now about math. Anyways, I don't want to talk about this. Okay, so this is the scenario that we would have with these quote-unquote word problems. So here's some examples and the answers that you can try at your own leisure. I won't be going over these specifically. The answers are here. You can certainly ask me on the discussion page or discussion board how to do these, but I'm hoping that you can practice with these. Now notice here I ask you to do solve these with substitution, solve these with elimination. The nice thing is that you can do both with each one of these. On the assignment or the midterm, I will ask, or I can ask, I should say, use substitution or use elimination. But if I just ask you to solve the system of equations, you can do whatever you want. You can use substitution or elimination. So hopefully now you have a common language with us. You understand how to solve equations, linear equations. You know how to solve a system of linear equations. And in their next unit, we'll be using the system of equations to get into some deeper relationships. Don't forget that there's homework posted. That homework is for you to try at your, however much you can try for your time commitment. But you also have the assignment that's due, and that's to be passed in, and I'll mark that. But the homework is just for you to kind of practice, and if you maybe need a lot of practice, you can do all of them. If you feel comfortable with this, maybe you don't need to do as much practice. But I will encourage you to practice your math. That's how you get better at it. That's how your brain learns it. All right, good luck. We'll see you next time.